Yeah, okay. So these two links should be familiar. If they're not, you need to look at those today, okay? You'll be needing to look at those today because those two videos have been posted up for the last few days. And rather than reinventing the wheel, I was doing a lot of looking for resources out there over the last week. And these are two very good videos talking about, first of all, continental drift theory from Alfred Wegener, and then plate tectonic theory. And I will go over those very briefly and very quickly because these videos have already covered the material. So if I go too fast at any time, just let me know. But I'm assuming you've already looked at this stuff. So basically, plate tectonics. We're going to get a little bit of the history here because in plate tectonic theory, it was built on prior theories, the main one of which was continental drift. So before we get into plates, what we're going to have to look at, see, this is a big plate right here. This is a tectonic plate. Remember, these plates are made of lithosphere. That means the crust plus the uppermost mantle. So they're going down, let's say about 40 miles or so on average between the addition of the crust and the uppermost mantle below it. Now, one thing that's interesting in this picture here is the yellow lines here show the boundaries of plates. So we can see that boundary, by the way, it means the edge, the border. So these are the edges of plates. And where the edges of plates hit each other, we see all kinds of stuff going on. So the red marks large earthquakes. And you see how the red and the yellow lines are pretty much in the same place. So we get big earthquakes, and in many cases volcanoes, we find that that's right where the edges of plates are. So where plates hit each other, where they border each other, the boundaries between those plates. That's where all the action is taking place. We also see that out in the middle of the Pacific Ocean here, the islands of Hawaii, we know we have volcanoes out there, but that's nowhere near the edge of a plate. So we have to explain what's going on there also. So this chapter will basically enable us to determine what's going on in creating earthquakes and volcanoes in all parts of the planet. And our understanding of that comes from plate tectonic theory. So first of all, what is a plate again? Well, those plates are, again, the crust and the uppermost mantle riding on the asthenosphere, the gooey layer of the asthenosphere. And tectonics means basically the building or the construction of these plates. So these plates get built, they get created in certain areas, they move from one place to another, and they get destroyed in other areas too. In this case, we see a divergent boundary and a convergent boundary. So plates are created at divergent boundaries and are destroyed at convergent boundaries. More about that to come. So, when did people first start having the idea that these plates could actually move across the planet? And we have to go back to probably the late 16th century, because at that point we now had accurate maps of the east coast of the US and the east coast of South America, also the west coast of Africa and the west coast of Eurasia. And we see that this S pattern right here for Africa's coastline and Europe's coastline matches the S shape of North America and South America. So for the first time when these maps were created, people could look at them and go, whoa, wait a minute, look at this. This thing and this thing look like they fit together. And this look like they fit together. As if these continents were torn away from each other by earthquakes and floods. So the first person credited with that is Abraham Ortelius in 1596. Not the only one to come up with the idea, but one who was widely accepted as speaking about it prolifically at the time. Now the idea looked like, hey, that's a good idea. It's a nice coincidence that they fit, but there's no way that ever happens. The world was created in a certain way. Well, the idea did keep coming back over and over and over again as scientific exploration and scientific thought progressed through the 17th, 18th centuries. We see this idea coming up in the 1750s, the 1800s, 1858. In fact, this drawing was done by Antonio Snyder Pellegrini in 1858, and it is showing that nice fit, that these indeed fit very well, these continents and maybe they were at one point together. But it was kind of like a ludicrous thought. It'd be like a crazy thought at the time to think that the Earth was that much different in the past than what it was in the present day. Well, that was until the 1912 to 1915, there were different publications. In English in 1922, the publication of The Theory of Continental Drift by this guy, Alfred Wegener. Now, Alfred Wegener was a German meteorologist and an astronomer, but he was interested in past climates and interested in the movement of rocks, or the potential movement of rocks, and how that might explain how some tropical coal deposits have been found in Greenland, and how some glacial features were found in what are now tropical locations. So to him, it didn't make a whole lot of sense from a climatic point of view, unless continents had actually moved. He read an awful lot, but again, he was primarily a meteorologist. Of note, his wife, Elsa, her maiden name was Köppen. And in fact, she was the daughter of Vladimir Köppen, the guy that we learned about from the climate section. His teacher was Vladimir Köppen. So he suggested that it doesn't make sense for the distribution of fossils on the planet, of glacial evidence on the planet, of specific rock types on the planet, paleo or old climate locations, didn't make sense unless some 225 million years ago, all the continents have bunched together like so, what we call a supercontinent Pangea. Just to check, you all following along, or anybody snoozing off already?
We're still here.
No, we're still here.
No.
Yeah.
Still here.
Okay, so he's saying that the continents basically drifted apart. It could have been the spin of the Earth, but they drifted probably from an equatorial location outwards. Who knows? But some force that drifted these continents apart. And therein, we'll see, lies the problem with his theory. Well, first of all, he was checking all over the planet, not only from his research in Greenland, but reading tremendous amounts of information coming back from people that were doing mining and resource extraction around the world, and looking at what rock types they had encountered. So basically, he found out that there were glacial deposits, or glacial evidence of like striations in the rocks, which are indicative of glaciers in South America, Southern Africa. And that would really only make sense if these continents were all bunched together some 220 million years ago. So glacial evidence, that's one thing. Fossil evidence was really compelling, though, because in certain rock types, as people were digging down into mines, they would find fossils. And they would look at what type of rock it was and how old that rock was compared to the rocks above it or the rocks below it. So the stratigraphy, or the layers of the rock, could be figured out. And when he looked at the evidence of certain fossils, like Cytognathus, only found in South America and Africa. This Triassic Lysosaurus, only found in Africa, Madagascar, India, and Antarctica. So only found in the rocks in those locations. Glossopteris is a fern tree. It has a very hard part. Glossopteris means feathery tongue because the leaves were hard, they were feathery in their look, and they're the shape of a tongue. And they're very distinctive, but they're found in the fossils in Australia, Antarctica, southern India, Madagascar, Africa, and South America. Now, what he was figuring was the only rational distribution of these is if you put these continents all together into this big supercontinent, because the Glossopteris fossils were only found in strata of a certain age, and all the same age, here, 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 and here. And then Mesosaurus, which is really it's a freshwater reptile that was found in the fossils of southern Africa and South America. Now, Mesosaurus can only live in freshwater environments. It cannot live in the sea. It cannot live in the ocean. It cannot swim from South America to Africa or vice versa. It could not swim. Again, only found in fossils of a certain age, certain structure, and only in those two locations. So it really only makes sense that these continents were bunched up like this some 225 million years ago. Rocks on one side of North America match those on the coast of Northwest Africa and Western Eurasia. So the mountains are pretty much the same here, like one mountain chain that have been torn apart. Basalt flows that came up to the surface, the same rocks in Africa match up with the rocks in South America. So basically, there's a lot of evidence here. Now, when he presented, when Wegener presented this information to geological organizations, they basically just poo-pooed the idea. Like, what are you telling us, dude? This is a whole different scenario from what we've been studying and preaching and teaching. And this doesn't make sense. And besides, you're a meteorologist. Go back to what you know. Don't tell the geologists what they know. So he was pretty much laughed off the stage in the 1920s. Now, he went back to Greenland to do some research. And as he was doing that research, he was outfitting little research cabins. So they were taking stock from one main base to others. And he got caught in a storm and froze to death in the ice in 1930. So when he died, he still knew his life's work had not been appreciated or accepted by the scientific community. The one thing he could not come up with is, how do continents drift? And that's what most of the geologists of the day were saying. Well, this doesn't make sense because continents cannot move. Well, it wasn't during his time that the idea would come about. But pretty soon afterwards, into the 1930s, we learned about radioactivity and the fact that radioactive decay takes place within the mantle. The rocks that existed in the Earth at the time of its formation are still decaying away radioactively and releasing heat. And maybe that's enough heat to make the layer below the crust into goo. Well, in the 1930s, Arthur Holmes, a geologist in Scotland, figured out that, yes, deep inside the Earth, we probably do have this release of radioactive heat, and that is making the mantle churn up and down and up and down. And maybe, just maybe, because of this convection within the mantle, that the crust on top of it can be moved in different parts. And therefore, maybe there's something to what continental drift theory was all about. Maybe Wegener was onto something. Well, as this idea starts to come about, something else happens in Europe in the end of the 30s, going into the 1940s, and that's World War II. So a lot less interest in did the continents move, and a lot more interest in blowing stuff up. So at the beginning of World War II, one of the most dangerous things to do was to be in a ship moving between North America and Europe, because ships from Canada and the United States would move towards, let's say, England, drop off supplies like tanks and cars and jeeps and lorries and rifles and ammunition and explosives and people. And during World War II, the Germans didn't like that very much at all. So as these ships would ply back and forth across the Atlantic, these underwater boats or U-boats would try to sink them. So at the beginning of World War II, to be in a ship was a very dangerous proposition in the Atlantic. These U-boats put a lot of tons of boats and people and supplies to the bottom of the ocean. Well, you got to find out where those submarines are. So shortly afterwards, we developed a system of sonar, which sends a compressive wave through the water and bounces off of a submarine and then bounces back, and you can have somebody with earphones on like this listening to the returning wave. So the wave will go out, so that return sound, there's something down there. There's something big and metallic down there. Well, sometimes it ended up being a whale. A lot of times it ended up being a U-boat. So once you can locate the U-boat, you can send depth charges over and blow them up, compress the hull, basically. So at the end of World War II, this was the most dangerous type of job to be in a U-boat, because now we knew where they were. We actually could intercept their communications also without them knowing. But basically, we could put an end to that threat or diminish that threat. Okay, now World War II is over. what do? We have a lot of ships. We have a lot of this sonar equipment, and we don't want to bring everybody back all at once, or unemployment would be horrible. So we also want to map out what's going on in the oceans. The other thing is we have a new enemy that at that point during the beginning of the Cold War was that with Russia, or the USSR at the time. And what we wanted to do was not let Russian submarines hide anywhere in the bottom of the ocean without finding them. So we not only had to use sonar to locate submarines, but also to map out the bottom of the ocean to see what we had and were there any hiding places for submarines. So we took the same ships and basically send that signal down, and it would bounce off the bottom of the ocean, and we would return that very weak signal. But if we do enough of this, it enables us to map out the ocean's depths. So basically, the longer it took for that signal to return, the deeper the water. So we were able to map out the oceans. And when we did this, we got quite a surprise. We did it in the Atlantic, we did it in the Indian Ocean, we did it in the Pacific Ocean. And what we found out was that as you move away from the coastlines, the water, yes, is deep, 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 deep. And then towards the middle of the, particularly Atlantic, we get this undersea mountain chain, boom, before we continue to very deep waters again. So this is called the abyssal plain. That's the bottom of the ocean, the big flat portion. But in the middle of the ocean, a big mountain system. And every now and then, that mountain system would poke up above the water as a volcanic island. So we know if the islands are volcanic, the whole chain is probably volcanic. Let's look at the Atlantic right now. So follow my cursor, and we're going down the Atlantic, and this is that chain of undersea volcanoes. Notice the shape here? That same S shape appears. So now we have an S shape on the coast of Africa, an S shape in the middle of the ocean, an S shape to South America, and that volcanic chain is pretty much in the middle of the ocean. We call those mid-ocean ridges. This one's in the Atlantic, so we call that the Mid-Atlantic Ridge. We also have one in the Indian Ocean, and we have one in the Pacific Ocean. In the Pacific, though, it's sort of towards the eastern half of the Pacific, so we call that the East Pacific Rise. The Atlantic one, being the youngest, is actually the most interesting because it matches the coastlines here. So, a former Navy submarine commander who was charged with mapping these out and was also trained in geology, came up with the theory of seafloor spreading. So Harry Hess came up with the theory that indeed these are areas of volcanism where the ocean is, where the crust is being ripped open by mantle convection. So it's ripped open, magma comes up, fills up that spot. That rips open, magma comes up, fills that spot. That rips open. So basically, what he's saying is the seafloor is spreading and pushing the continents aside. And if you go back in time, when this was first happening, these continents would have been together. Well, what do you need in order to prove that? You got to prove that the rock at the bottom of the ocean over here matches the age of the rock on the bottom of the ocean over here. Now we have to wait another decade or so, or later in that decade, before we had the technology to drill down into the ocean and find out if indeed, by taking samples, is the ocean floor over here getting older and older and older and older as you move away from this spreading center in the middle of the ocean, and older and older and older and older as you move in this direction, and the rocks on one side match the age of the ones on the other side. So to do that, you got to drill down and take samples of this ocean floor. And we weren't able to do that until the late 1960s, but at that point we were able to do it by having a floating ship with a drilling platform on it, owned by Global Marine Company. And we were able to utilize that to take samples across the Atlantic Ocean on both sides of the spreading center and obtain dates from them. We obtained the dates by getting the rock samples and looking at the relative abundance of certain types of rocks and the parent material compared to the daughter, the isotopes that are basically created as the rocks decompose. So what we find is right here along the edge or the ridge, this mid-Atlantic ridge, the rocks are pretty new. As we move further away, These rocks here, 50 million years old, 50 million years old. 100 million years old, 100 million years old. 200 million years old, 200 million years old. So basically, when these 200 million year old rocks were formed, and these 200 million year old rocks were formed, they were located at the same place. They were located here. So the Atlantic Ocean split and started moving apart. The Atlantic Ocean got bigger, the continents were being pushed apart. So finally, we have the evidence to put a whole theory together. We took the evidence of Wegener's continental drift. Convection provided a mechanism, mantle convection, that allows us to visualize a mechanism for these continents to actually move. Sea floor spreading, it tells us that it occurred in the middle of the oceans and basically pushed the continents aside. The data that we got from the age of that proved that that was going on. And so we have a valid theory called plate tectonic theory. So what indeed happened? 225 million years ago, we did have this supercontinent called Pangaea. The northern portion was called Laurasia, and the southern portion, I love this name, was called Gondwana land. And since then, they've been splitting apart into our current configuration. So this is 225 million years ago, 200 million years ago, 135 million years ago, 65 million years ago, and present day. And one thing to notice, just 65 million, let's go to 135 million years ago. There's India. By the way, Antarctica and Australia connected at that point. 65 million years ago, India is slowly moving north. Australia and Antarctica about to split apart. And now today's Antarctica over here, Australia over here. What happened to India? Oh, there it is. It went boom into Asia, creating the Himalaya range over here. So that's pretty cool stuff. Alfred Wegener was right. What's happening is the oceans are being split open. Here we have continental crust, oceanic crust, the rigid mantle, making lithosphere. We have these lithosphere plates. Some are all continental, some are all oceanic, some have a bit of both, and they're riding on the convection going on in the asthenosphere. We have a lot of big plates, about 7 big plates, and lots of tiny, tiny ones. There's probably about 20 to 25 total plates. They are gliding around on the top of the Earth, driven by the convection cells below them in the asthenosphere. One thing of note here, wherever the edges of those plates are, that's where the action is for the most part. And these plates, they can be ripped apart from each other, they can move into each other, and they can slide past one another. But wherever the edges are, that's where we got to focus to find out what's going on this planet in terms of earthquakes and volcanoes. These are the directions of the major plates. These arrows are showing which way they're moving. Keep in mind, here's the Pacific plate. We actually live on the Pacific plate. It's hard to see, but we're on the edge over here of the Pacific plate, and we're moving northwest. There's a line that separates the Pacific from the North American plate over here, and that line is called the San Andreas Fault. That marks the plate boundary between the Pacific plate moving northwest and the North American plate moving west. And as those two slide past each other right where we are, that creates the San Andreas Fault. Again, more on that to come, because we have to talk about these edges of plates, again, where all the action takes place. So our plate boundaries or plate edges come in three different varieties: divergent, convergent, transform. Before we go any further, anybody have questions? Because this should be a bit of a review based on what the videos showed us, but there's bound to be some questions.
No questions.
Are we all good?
Yeah,
okay.
Pretty good.
Yes.
All good? Okay.
I do have a quick
Now,
question though.
Yes.
I think it might relate back to a past chapter. But okay, so because California is like so overdue for a big earthquake, like could that result into like a larger movement of plates because of that?
More so the other way around, like a movement of the plates would actually give us a large earthquake.
Right.
And it is a good question because we look at around the Pacific, the northwest portion of the Pacific out by Korea down through, let's say Japan, that's had lots of big earthquakes. The southwest portion out by Indonesia, lots of big earthquakes in recent years. On the Pacific now, we're looking at the southeast, so the coast of South America, lots of big earthquakes. Then we look at the northeast portion of the Pacific out by California. Maybe I should look at this slide here. So I'm looking at out here. We haven't had many big earthquakes. So we could very well be overdue, or the rocks here are not strong enough to build up to very big earthquakes, and instead we get lots of smaller earthquakes. Well, we know the rocks here are big enough to give us large earthquakes, and it's been a while since we've had any big ones out here. In fact, 1906 in California, we had a pretty big earthquake. The last time we've had one in the southern portion of California that was massive was 1857. 1857 is over 160 years ago. And those things are supposed to break about every 90 years or so in our neck of the woods. Hasn't happened. So yes, we could be overdue. So what can we do about it?
I mean, the way I see it is like we either have like this large like piece of pressure that's just waiting to like let go itself, or we have small multiple pockets of pressure that just start like rumbling to small earthquakes. Is that right?
Yeah, so you would either get lots of earthquakes that are magnitude 6 or 7 every 10, 20 years, or you would get some very big earthquakes, magnitude high 7s, maybe even 8, maybe every century and a half. It's like a rubber band. If you pull a rubber band, right, pull it and snap, pull it and snap, pull it and snap, pull it and snap. Well, that's not going to hurt your finger. But what if you pull, bam! When it snaps, whoo, it's going to hurt. And that's kind of what the rocks are doing. We have rocks on one side of a fault and another side of a fault, and they're moving past each other. I'll do it this way. They're moving past each other. But they're sticking. And as they stick, then they're going to break. So the rocks, the angular nature of the rocks, they kind of stick, and then they'll break. Just like a rubber band. Pulling that rubber band, if you keep on pulling, it hasn't broken, keep on pulling, at some point it's going to break. And that's what we're going to experience at some point along this portion of the juncture between the Pacific and the North American plate.
Interesting. Okay, thank you.
There's nothing we can do about it. Nothing we can do about it. It is going to happen, but it might not be in our lifetimes. It may be after. It may be tomorrow. We just don't know. Because all these processes act in geologic time, not human time.
Right.
So 3 plate margins. Plates are either going to move away from each other, they're going to move into each other, or they're going to move side by side. So we break that into divergent boundaries, those that move apart, like in the mid-ocean ridges. Convergent, that's when plates come together. And we'll see that there are 3 varieties of those. And there's also transformed, the ones where they move side by side, like the San Andreas Fault. And this is where this discussion differs from that of the video you saw a little bit. I'll explain that. First of all, divergent boundaries like those on the seafloor is where we have convection in the asthenosphere, and it's going to drive the crust in different directions. So this crust is being pulled in this direction, and this side is being pulled in the opposite direction. That opens up a crack in the crust and uppermost mantle. Magma comes up, fills that spot, and solidifies. But the convection is still going on. So after a little while, this thing will crack again, and the 2 new sides go in the opposite direction. New magma comes up and fills that gap. That will crack open. So it's a continuous process of magma coming up, solidifying, well, magma coming up as lava, solidifying into igneous extrusive rock and then moving in opposite directions. So this is very indicative of what's going on in the middle of the seafloor. So we call it seafloor spreading, right? But it's basically a mechanism from that convection going on in the asthenosphere. So this is a divergent boundary. Diverging means going in opposite directions. So the mid-ocean ridges, like the Mid-Atlantic Ridge, is a great example. Now, if things move apart on a oblate spheroid, at some point, the stuff moving in this direction is going to bump into stuff, and it tends to bump into continents. So we can see here that material, that crust and uppermost mantle, moving in one direction will bump into other stuff. So here we have a divergent boundary, but over here we can see a convergent boundary. This crust and this crust converging to one another. I want you to focus on this portion for this diagram right now because we're focusing on the divergence or divergent boundary. Number one example of that, the Mid-Atlantic Ridge. We do see divergence take place over land also. The eastern portion of Africa, with the continent of Africa being split apart and the eastern portion opening up these deep, deep valleys. It's very hard to split a big chunk of continental crust, but not impossible. So Africa is slowly being broken up. It's being rifted. And that's why we call the East Africa Rift or the Rift Valley, often filled with lakes like Lake Tanganyika, Lake Victoria. So divergent boundaries, they can occur over the land. We call those rift zones. They can occur more often in the oceans. Again, it's easier to rip thin ocean crust than it is to rip thick continental crust. Our second type of plate boundary is called convergent, and they come in 3 varieties, and these are the names I want you to know for those varieties, okay? And it all matters what type of crust is being converged. So we can have oceanic crust bump into continental crust. We can have oceanic crust bump into oceanic crust. And we can have continental crust bump into continental crust. Instead of saying bump into, I can now say converge with. So we can have oceanic continental convergence, like in this diagram right here. The ocean crust is thinner and more dense. So when these 2 types of crust converge, the ocean crust always loses a battle and gets thrown down deep into the earth below the continental crust. That process of one piece of lithosphere being thrown down below another is referred to as subduction. So subduction is a process. When subduction occurs, we often get an offshore trench. That's a deep, very deep low spot off the coast. But because of weathering and erosion, sediments tend to fill in that trench. So the trench is being made deeper by the subduction process, but partially being filled back in by weathering and erosion and deposition. Now, what's going to happen is, as that subducting plate goes lower and lower, it's going to grab some ocean water with it. It's going to grab some of these sediments with it. And the ocean water plus the sediments plus the subducting plate partially melts that plate that's being thrown down deep into the earth where it's hotter and hotter. So that's going to partially melt, and plumes of magma will come up, some all the way to the surface, and form volcanoes on the continent. So we get a line of volcanoes on the land referred to as a volcanic arc. So volcanic arcs are always on the land, just like the Andes Mountains in South America or the Cascades that run from California through Oregon and into Washington in North America. Our second type, oceanic. Here we see ocean crust converging with ocean crust. One of them loses a battle and gets subducted below the other, partially melts, and that magma comes up, extrudes as lava on the surface, making a line of islands, because this is out in the water now. So we call this an island arc. This is how the islands of Japan, the Philippines, Indonesia, the Caribbean, they're all made this way. So they're called island arcs. So we would see a very deep trench in this case, ocean crust already lower, bumping into ocean crust, forming a very deep trench like the Marianas Trench, with these lines of islands called island arcs running parallel to the trench. Still, that process is called subduction. So in both cases, we have subduction. This is where it differs from that video you saw. The author of that video referred to this as a subduction plate boundary, and this is an island arc plate boundary. Well, subduction is a process. An island arc is a process of oceanic-oceanic convergence, where a volcanic arc is a product of oceanic continental convergence. So these are indeed the names of the plate boundaries. Subduction occurs in these two processes. One forms an island arc, one forms a volcanic arc. Our last type is called continental-continental, and of course that's continental crust bumping into continental crust. One tries to subduct, but because continental crust is so light, it can't subduct, and it basically crumples up and forms a mountain chain. The most famous example of that is the Himalayas. So here we see the formation of an island arc, like in Indonesia. We have a trench right here. We have subduction taking place, partial melting, forming of volcanoes. Those volcanoes form a line parallel to the trench out in the water, so that's called an island arc. For, again, Indonesia, here's the islands of Indonesia, at least the southern portion. This is called the Sunda Banda Arc. That's Sumatra, Java, Bali, Lombok, Sumba, Sumbawa, Flores, Timor, etc. All these islands right here. What's happening is this ocean crust here is subducting below this oceanic crust over here. This line tells you where the subduction is taking place. So right there, there's a trench. Now that means that we have ocean crust and ocean crust. The trench is occurring here. Now that plate has to go deep, 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 deep before it melts and comes up as magma. So it takes probably 100 miles, in this case, 50 to 100 miles, in order for that plate to subduct far enough and then bubble up those plumes of magma to form the islands over here. So this process is occurring right here. If you ever want to go to Bali, let me know once travel's opened up. We built a research station out there for culture a number of years ago, and we always take students out there to go see it. One of my favorite places on the planet. Okay, our last type of plate boundary is transform plate boundary. Here we see the Pacific plate and the North American plate. When two plates slide past each other, when they're sliding past, that's a transform plate boundary. So the Pacific plate is moving northwest. Whoa, I just moved the slide there. Sorry. The Pacific plate is moving northwest, and the North American plate is moving west. Because this is moving northwest, this is moving west, the only difference is that one appears when they bump past each other, that one is moving north and the other one moving south. In actuality, they are both moving somewhat west, but this one is moving northwest. So the line that separates the two plates runs right across here. So Glendale is right around here where the cursor is. If we go to the east, we see that line called the San Andreas Fault running down from like the Palm Springs area all the way up through San Francisco and beyond. Everything to the west of that line is in North America. Sorry, everything to the west of that line is on the Pacific plate. Everything to the east of that line is on the North American plate. So we're on the same plate as the rest of the Pacific. Whereas we go to the east, this is all on the plate connected to the rest of North America. And that line is where the pressures build up. Every year, this should be moving about 2 inches towards the northwest relative to this. But it doesn't because the rocks are so strong they don't let it move. So it wants to move, 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 can't. All of a sudden, bang, it's going to move all at once. The last time this area broke was 1857. So we have about 160 years of 2 inches per year to catch up. That means that when we do finally move, the basement rocks way below us are going to try to move 25 to 30 feet in 1 or 2 minutes towards the northwest. And that is going to really wake you up if you're in bed.
When will that be, though?
No. If I could answer that question, I'd be a billionaire. We don't know when they're going to move. We're trying to develop warning systems now because when we actually do have that motion, it might take 30 seconds or so for the shaking to reach far away places. So we can let those places know and say, get under a table now because 10 more seconds and you're going to start shaking. And the thing about earthquakes, if you don't put yourself on your butt, the earthquake will put you on the butt. Okay, so we can see the breakup of Pangea because of these convection cells slowly moving to our current positions. And now we know very much why and what type of features will be created. Over here we have a divergent boundary. Over here we have convergent boundaries. We can explain a little later on what kind of features will be created. Now the thing we cannot describe with plate boundaries is how the Hawaiian Islands form. If I go back here for a second, the Hawaiian Islands are out here in the middle of the Pacific Ocean. There's no plate boundary anywhere near them, yet we still get these volcanoes. The reason for that, as we end this lecture, is that we have this very, very hot spot within the asthenosphere. And as the magma plumes rise, they're so hot they don't convect. Instead, they burn a hole straight through the uppermost mantle, straight through the crust, onto the ocean floor, and they start to build up a volcano. So basically, that volcano is directly above the hot spot in the mantle. So we call those stationary hotspot mantles, or mantle hotspots, or hotspot. So there's a hotspot. It doesn't move, but it does send lots of magma up, burning a hole to form an island. Now, in the Pacific, the crust and uppermost mantle are moving towards the northwest, but this hotspot stays put. So what's going to happen is the hotspot will form an island. The hotspot's not going to move, but the island then moves, and then a new island will form, and then that will move. Then a new island will form, and that will move. So we get a chain of islands going from forming right now, formed 1 million years ago, formed 2 million years ago, formed 3 million years ago. And because they move away from the hotspot, which is kind of bulged up a little bit in the asthenosphere, and because of weathering erosion, as they get older, they get worn down. So if we were to look at the Hawaiian Islands, here's a big island of Hawaii right now with its active volcanoes. The big island has a lot of internal processes building it up, and weathering and erosion only just started to flatten it down. So the big island is big, and it's currently still having eruptions adding lava to it. The Pacific crust has moved in this direction. 2 million years ago, Molokai was formed. 1 million years ago, Maui was formed. 5 million years ago, Kauai was formed. When Kauai was formed 5 million years ago, Kauai wasn't located there. Kauai was located here. So we got a volcano forming, the crust keeps moving, that volcano moves over here. A new volcano forms, and it moves. A new volcano forms, and it moves. So we can backtrack 5 million years ago, 3 million, 1 million, today. And if we look at this whole area from Kauai to the Big Island, that falls into this little box right here. So if we keep going off, whoa, way out here, we can go all the way to Midway Island, probably some 20 or so million years ago. Midway Island was being formed by an active volcano that was located right here. So that's why certain places that aren't at plate boundaries can get volcanoes. And typically that's, the answer to that would be, it's got to be a hot spot below those islands. So Hawaii, certainly a hot spot. We have the same thing going under the continents too, in Yellowstone. So Yellowstone, we do have active volcanism over there. We know that from the hot springs and geysers. But 2 million years ago, 6 million years ago, 10 million years ago, 12 million years ago, we have volcanic eruptions that were occurring in what is now Idaho. And those, when they erupted, were actually located over the hotspot that is currently under Yellowstone. So as the continents move, and we have hot spots in the mantle below them, which don't move, it's going to show us progressive series of volcanic eruptions millions of years apart in many cases, because the volcanoes are not constantly going. All right, this parallels what was talked about in those videos. You have everything now to master what is going on with continental drift, plate tectonics, and plate boundaries. Just remember, in the videos that you watched before, the convergent plate boundaries are not continental, subduction, and island arc. Those were misnamed in the video. The three types of convergent plate boundaries are continental, oceanic, and oceanic. Two of those, the ones that involve oceanic crust, involve subduction. And that subduction will create either an island arc or a volcanic arc. Okay. There's a lot to chew on. There's a lot of information there. In terms of plate boundaries, what kind of questions might I ask you on a test? None? Anything? Class?
Can you repeat the question?
I can swear, yeah, what kind of questions might I ask you on the test about plate boundaries?
You could ask what is associated with divergent boundaries, with convergent boundaries, and transform boundaries.
Okay, so I could say something like this. The islands of Indonesia are represented by this type of plate boundary. Or the islands of Indonesia are formed by this type of plate boundary. What would be the answer for that? Would it be divergent? Would it be convergent? Would it be transform? Convergent, yeah. So the islands of Indonesia are formed by a convergent plate boundary. Anybody be more specific? What type of convergent plate boundary might that be?
Oceanic.
Oceanic, very good. Oceanic convergence is what forms the islands of Indonesia and Japan, the Philippines, etc. Now, when that occurs, one portion of oceanic plate gets thrown down below another portion of oceanic plate. What's that process actually called, that throwing down of one plate below another?
Subduction.
Yes, subduction. Very good. Subduction. Excellent. And when that subducted slab goes down deeper and deeper and deeper into the earth, it gets hotter and hotter and hotter, it will partially melt. Magma will come up to the surface, now as lava, forms an island on the bottom of the ocean, or chain of islands, because this is a sheet of magma going in. What do we call that chain, that type of chain of islands formed by oceanic convergence? They refer to it by or as an island something. It almost sounds biblical.
Island arc?
An island arc. Yes. So an island arc. In this case, an arc just means line.
Oh.
A line of islands. An island arc means a line of islands formed by oceanic convergence and then subduction. Okay. Those are the types of questions I might ask you a question about. Subduction, about how the Indonesian islands formed, about what we get when we have oceanic convergence, this island arc. If instead of having oceanic convergence, we had oceanic continental convergence, what kind of arc forms on the land there? It's not an island arc, it's something else, like the Cascade Range of North America or the Andes of South America. It sounds almost obvious, but we don't call that an island arc, we call that a volcanic arc. So as we go through the slides, make sure to take a look at some of the terms that we looked at in that regard. So I want to show you what I'm talking about. This mountain range, with oceanic continental convergence is called a volcanic arc, whereas with oceanic convergence, we have an island arc. Okay? That's where I got those terms from. Okay. It is 10:27. We're done with the first part of the chapter. I did record this, so I'll be able to get a copy of the Zoom recording for this lecture, which also went over the answers to that prior quiz. Don't forget that you have until 11 p.m. to take that quiz again. I made it 5 times because I extended the time to 10 minutes instead of 6.
Oh man, I took my last.
And no, you can do it again.
I mean, like 6 minutes is too short for 10 questions.
Yes, exactly. That was my mistake. That's why you can now take it up to 5 times, and you'll get 10 minutes for the remaining ones. Okay.
Well, I got 9 of 10, so.
Well, you did pretty well then. See, 6 minutes wasn't too fast. You did perfectly.
Well, I
Took an
made
A on
a lot of questions for the first time.
it. Well, go ahead and take it one more time because you'll probably get the same ones right, and you might get the extra one right with that extra minute or so.
Okay.
All right, everyone. So I will post up the second portion of this chapter. I've already done it. It's rendering as an MP4 right now. I'll upload that within the next hour and a half. So if you want to get a jump on Monday's lecture, go ahead and take a look at that. We will have a quiz on Monday. So Monday's our last chance for questions before we have our final, which is 1 week from today, believe it or not. So try to be ready and fire off questions if you have them. Send me an email. I'll get back to you as soon as I can. Okay?
We're going to get a study guide for.
Well, your study guide for chapter 7 is actually the climate data worksheet.
Okay.
So if you fill it out, that's your study guide. Now, to tell you the truth, there is already a study guide for these chapters. I hid it in the textbook, but I'll pull it out and I'll post it up. Okay? Make sure you've got everything. So I will do that later today also.
All right. Thanks.
You're welcome. All right, everybody. I'll see you on Monday, but don't hesitate. Fire off if you got any questions at all. Okay?
Okay.
Thank you, Professor. Bye.
You're very welcome. I'll stop that sharing there. Okay. All right. Take care, everybody. If you have questions before 11 p.m., what's still going on? If something's not clear, fire off an email. I'll try to get back to you right away. Okay? Bye. We'll see you soon. Take care.
All right, bye, Professor.